information in there. Version 2, exam, that says exam 7, but it's really exam 6.
Yeah, it's because that one before said EXAM5.
Yeah. Okay. Number 2.
I'm gonna say EXAM4.
I'm sorry.
I said it said EXAM4 and it was EXAM5, I think that's what it was.
Yeah.
So they've all.
I think at one time I had a couple of chapters separate exams. And then later on, I combined 2 of them. I think it was actually the first 2 chapters.
Yeah.
I combined them into one test, and then I forgot to change the review document numbering. Okay, a 2-bulb flask contains 5 particles. So that. So we've got 5 particles in here. At that point, they're all on one side. What's the probability of finding all 5 particles on the left side? What's the probability of finding 1 particle on one side? It's either this side or that side, right? So it's 1/2 is the probability of finding it on one of the other sides. And then what's the probability of finding the second one on one side or the other? It's another 1/2. And then the third one, it's another 1/2. And the fourth one, and the fifth one. So the probability of finding one is 1/2. Probability then of finding the other one is another 1/2. So it's 2, let's see, 1, 2, 3, 4, 5. It's 2 to the 5th power. 2, 4, 8, 16, 32. So the probability is 1/32. Or, where's my calculator? Since it's given in percentage, I have to calculate it. If it were in fractionals, then we'd be done. 3.13. 3.13%. Oops. There we go. That's the probability of finding all 5 of them on the left-hand side. Maybe the same probability of finding all 5 of them on the right-hand side. Second law of thermodynamics states what? That's the one that talks about entropy. Right. The entropy of the universe is what? Let's see, number 4. The change in entropy for the entire universe is always increasing. That's one way of saying the second law.
It's an enthalpy that doesn't change. There's no more. What is it about the universe?
Oh, this is the second law. The first law just says the change in energy for the entire universe is 0. In other words, the amount of energy you start with is what you got now. Yeah. Another way of saying this, I think we derived the Gibbs law from the second law, right? Delta G equals delta H minus T delta S. Maybe that's the one you were thinking of. Enthalpy minus temperature times the entropy is equal to delta G. Okay.
What was 4?
That was 4.
Yeah, what?
Oh, the letter D. Yeah. And 9 is A. Let's make some room here. Tried to make this board cooperate by cleaning it real good and then put WD-40 on it. Helped a little bit. At 1 atmosphere, liquid water is heated above 100 degrees. So if the pressure is equal to 1 atmosphere and the temperature what would be the result in terms of thermodynamics if the temperature were at 100 degrees? Right? The water would be boiling, we'd be at equilibrium. And the change in the total change in entropy at this point would be zero. That's always the case for equilibrium. Okay. But if we heat it above temperatures greater than 100 degrees, now we've got an endothermic process. Right? We've got a system, which is the water that's boiling, and we're extracting energy from the surroundings to increase this temperature above its equilibrium point. So we've got delta H is going in, which is positive, and delta S for the surroundings now is decreasing. Yes. So let's see. Delta H for the system then is increasing. It's greater than zero. This is less than zero. This would be greater than zero. Because now it's not an equilibrium process. And it's not at equilibrium. We're actually,
You could say,
now I was going to say something I better not, because it might not be right.
stick fully.
Yeah, I better stick to the program. All right, number 9 is A. Number 14. For the process, CHCl3, CHCl3, which is, what is that? Trichloromethane. Yeah, solid. And we're going to liquid. All right. We're told that the delta H is 9.19 kilojoules under standard conditions. Kilojoules per mole. And we're also told that the delta S, 0, is equal to 43.9 joules per K mole. Okay. Chloroform. What's the melting point of chloroform? All right. Melting point means that we're at equilibrium. So when you're at equilibrium, you can say, remember we had delta H for the surroundings equals minus delta S. Wait a minute. What's the other way around? Delta S. Yeah, I got it backwards. Delta S for the surroundings. Here we go. Is delta H over T. At equilibrium, we can say also that delta S for the system is equal to the positive delta H over T. We can do that for equilibrium, because there's no exchange between the system and surroundings. So one is the other one is equal to the other one with a different sign. So with that being said, we can find out what the boiling point is, melting point, excuse me, melting point. What we need to do is solve for T. And bring T over here, delta H over delta S system. So delta H is, and these have to be in the same unit. So this is 9,190. 9,190 joules per mole.
That's kilojoule.
Yeah, but they have to be in the same units. Yeah, so we change this one to joules. And leave this one as joules, 43.9 joules per K mole. Moles cancel, joules cancel, and we're left with K. And K, the denominator of the denominator is the numerator. So this K flips up in here. So 43.9 divided into 9190 is 209.3. 209.3 K. Let's see, our units are in C. So minus 273 is minus 64 degrees C.
Hey,
Yep. The only reason we can do that is because we're at equilibrium. All right, what's next? Here we go. Number 20. When I came in here this morning, it was writing all over the board, and it looked like geography or geology. Does George, does he teach a physical science class?
so he teaches astronomy, he teaches biology, and he doesn't teach physics. Nobody wants to take it. So he doesn't teach physics. I'll teach physics this semester. Because he's gonna teach physics 2 class because he had this boy from Marshall Neiman, and he asked me if I wanted to take it. And I told him if he taught it, I would, even though it was so hard. But I learned so much. I told him I'd take it. And he was like, okay. Well, that boy didn't want to take it anymore. And he was like, Mom, I'm just not going to take it. He doesn't want to teach it because they won't pay me. I said, okay, it's fine. He taught me for free last semester.
Oh.
They wouldn't pay me because I was the only student in the class.
They wouldn't pay him?
So at the end of the semester, I bought him $100 gas card. I felt bad.
Yeah. Well, that's what we do at New River. I mean, if you have less than 3 students, they pay you per student, $100 per student. That's it.
Yeah, they should have paid me. I mean,
Yeah.
that's ridiculous.
Well, I was just curious because they had all this writing up here that looked like geology. And he had the time scale for the Earth and all the epochs.
That's probably, he teaches astronomy, so
Maybe
he teaches a physical science class too.
that's it. Physical science.
Yeah.
Yeah. Okay, 20. In which case must a reaction be spontaneous at all temperatures? All right. The best way to do this one is to use Gibbs equation. Right? And if we want the reaction to be spontaneous, free energy has to be negative. Okay? So when will it be free negative? Under all conditions of temperature. A situation where you can have this term is negative and this term is negative. So in that case, we would have an exothermic reaction that has a positive delta S. And that would always give you a negative. So let's see, D. Delta H is negative, delta S is positive. Doesn't matter the temperature, it's always spontaneous.
Is that because the system gives up heat?
No. No, I mean, we're working from the
Oh,
equation.
because it's spontaneous?
Yeah, we want to know, we want to be sure it's spontaneous no matter what the temperature.
Okay.
The only way to do that is to guarantee that this one's negative and that one's negative. If one of them is positive, then the temperature influences the balance between the two. But if they're both negative, then that's always negative, and that occurs when this is positive times a negative, and this is negative. So exothermic and delta S is positive.
Okay.
Let's see. 26. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of H, S, and G? A stable diatomic molecule. We have a diatomic molecule. And when we're talking about in these terms, always make it a gas. Because if you do that, then you're not dealing with phase changes. Spontaneously forms its atoms. So it goes to 2 X's in the gas phase. If it's spontaneous, delta G is negative. We know that.
Yeah.
So then we have to look at which side has more energy. This side is higher energy than that energy because the diatomic molecule is more stable. So we can say we had to add energy in to get it to do this. That means,
The right side's more, because you added,
yeah,
okay,
yeah. Usually the separate atoms are higher energy than when they bond together.
Okay.
So in that case, we had to put energy in, and delta H has to be positive. Okay. So delta S, we can calculate. Well, maybe we can't calculate delta S, but we can reason delta S because this is 1 mole and this is 2 moles. So delta S is positive. You're going from 1 mole of particles to 2 moles, right? More disorder. Right? Because you've got the same number, you got say 1 mole of the diatomics here. Now you've got 2 moles in the same space. That means the number of microstates had to increase in order to accommodate them. So delta S should be positive. So let's see, it's H, S, and G. H, S, G. So it'd be positive, positive, negative. Positive. No, it says they're all negative. Why is that? Delta G is negative. Spontaneously. Let me see what I'm doing wrong. 26.
when a stable diatomic molecule,
We know that delta G has to be less than 0. Oh, wait a minute. I got it backwards. A stable diatomic forms from its atoms. I got it backwards. The reasoning is right. I just set it up wrong.
so it goes backwards.
Here. This is the way the problem is given to us.
So it's,
A stable diatomic molecule spontaneously forms from its atoms.
so it breaks.
Goes this way. It forms the bond.
So it breaks apart like it.
No, it makes the bond. It's like you got this separate plus this separate forms this diatomic. That's what we're saying. These are separate atoms. They spontaneously.
I thought you said the coefficient 2x. I thought you said that was the one that was formed together.
I had it backwards.
Oh, okay.
Yeah, that was my mistake. I read the problem wrong. A stable diatomic molecule spontaneously forms from its atoms.
Okay.
Okay. All right. Now let's go back and look at it again. We know that that delta G is negative because it says it's spontaneous. And then we also know that this is more stable than that. All right. So it gives up energy when these two atoms come together. That means this has to be negative. And This is 1 mole, that's 2 moles. It's becoming more ordered, which means delta S is also negative. Okay.
So when they form, they're negative? Like when it comes together?
Which one? This one?
Yeah.
This one?
S.
I'm looking at the number of particles in the same space. This one has 2.
So
2
it's
moles.
decreased.
Right, you're decreasing the number of particles.
Okay.
It's becoming more ordered.
Okay.
So delta S has to decrease.
So if there's more number of particles, then that's positive. And then the less, the more they can join, that's the more negative. Right?
Right, when you're looking at a balanced equation, that's a good way to look at it.
Okay.
Yeah. So if we had, say, hydrogen gas plus oxygen gas yields water, and I'm going to make this a gas also, then in order to balance this equation, we need 2 here and 2 here. We have 1 plus 2 is 3 moles over here. We got 2 moles over here. So delta S is going to be negative. You're going from 3 to 2. Fewer moles from 3 to 2. So delta S for this one should be negative. Now we know that delta H is also negative. Right? When you put hydrogen and oxygen together, you release a lot of energy. So that's definitely exothermic. And it's spontaneous. So this one would also be negative, negative, negative.
Okay.
All right. Let me see if I can do this one without messing up. All right, 31. Calculate KSP for the salt, sodium chloride at 25 degrees. All right. The KSP for sodium, oops. Try that again. Solubility product. So we have sodium chloride, solid, goes into solution as sodium aqueous and chloride aqueous. And we want to find out what the KSP is. What's the solubility product? All right. The data we're given here is only delta G. So we can use the relationship here. The delta G for this reaction under standard conditions would be, right, the sum of the delta G's of formation for the products minus the delta G for the reactants. Okay, so we can find out delta G. And where I'm going with this is delta G 0 equals, let's see, K, excuse me, T, RT, excuse me, RT log K. Is there a negative sign in front of that? Yes, there's a negative. I thought there was a negative sign. Okay, so that's where we're headed. We're going to use this formula, but we have to find out what that delta G is. All right, so from the data we have, we need products. So we have sodium and chlorine, minus 262. And then the other one is minus 131. And then minus, what's the reactant? Minus 383.8. And this is in kilojoules. Yeah, these are in kilojoules. Okay, let's see what's that number. And that's equal to delta G0. The delta G's and the delta H's are usually in kilojoules and the delta S's are in joules. So that's one place you could trip up. 262 and 131 and then plus 383.8. So I get minus 9.2 kilojoules. So if we say, and that's equal to delta G 0 equals negative 8.3145 for the R. And standard temperature would be 25 plus 273. Times log K. And we can solve for K. All right. So if I say this one divided by that one divided by this one is equal to log K. And so minus 9.2, I already got it in here, minus 8.3145, divide it into that, and then divide this into it, which is 298. And I get 3.713 times 10 to the minus 3.
What'd you?
I divided this one by that one, and then divided that
Number, that's something.
that quotient by this one. So I'm putting both of these over here on this side.
Okay.
Okay, and that's what I get. Divide this one by that one and divide by that one. And I get this value. So K is equal to E to the 3.713 times 10 to the minus 3. And K, I get K is 1.004. That doesn't look right. 25 degrees. I used the right 25 degrees here.
It's
Okay, I divided wrong somehow. Oh.
one.
Oh. This is joules per K mole. And this is kilojoules. This has got to be minus 9,200. All right, so this is going to be 10 to the minus 1.
Question.
Yeah,
Why do you have one times negative 262?
where?
Like on here, on this,
Oh, on the work problems?
yeah,
Oh, that's because there's 1 mole of each.
okay. And then you have them separated, like, see, and then plus, and see times those?
No, that's plus.
Okay,
So it's 1 times that because there's 1 mole of it. There's 1 times that because there's 1 mole of it. 1 times that because there's 1 mole.
okay.
And then I had to change this. I forgot to change that to joules because this value here,
This is just joules.
that's kilojoules.
Wait, that's kilojoules? That's-
Yes, that's
Okay.
kilojoules,
Okay, there's the K.
kilojoules. And the reason I have to change this to joules is because of that constant is joules per K mole.
Okay. All right.
So if I do that, then E to the 0.3713.
Have a real problem with units. It makes me so confused.
This is 1.45. And that's still wrong. Let me try it again. Okay, 9,200 and 8.3145 and 298. Oh. Here we go. I was off by an order of magnitude. It's E to the 3.713. 4.1. Or 4.10. There we go. Took me a while. No, that says 41. It is 41. Yeah, read my calculator right.
How long does it take you to write these out?
Not too long if I do it in a quiet place.
Because they're actually helpful. I don't know if Mahalia or if I use them, but I go back through and I fill out the whole review with this
Uh-huh,
so I understand it.
uh-huh.
I don't think they do that, but I do that. And it helps me because sometimes like you put different stuff in the exams, like on the.
Oh, yeah.
Put like 2 or 3.
Change the parameters. Yeah. Yeah, if you know how to solve the problem, then you can get the answer. But if you just memorize the answer, you would be in trouble.
Yeah, but they're helpful, kind of.
Good.
I don't have time to study. I hardly ever have time to study, so like I try to be study very effectively when I do have time to do it.
Oh, yeah. Yeah, use your time efficiently. 34. Let's see. I'm not doing too good today. Consider the gas phase reaction. NO plus a half O2 yields NO2, for which delta H is minus 56.91 kilojoules, and K equals 1.46 times 10 to the 6 at 25. For this system at equilibrium, how will raising the temperature affect the amount of NO present? All right, so we have NO, gas, plus a half O2, gas, yields NO2 gas. NO2 gas. And we're given delta H, 0 is minus 56.91 kilojoules. And we're also given K, 1.46 10 to the 6th. Well, that tells us that the equilibrium is way over here. But this also tells us that it's exothermic. Right? This negative value tells us that the heat term would be on this side. All right. So for this system at equilibrium, what happens if we raise the temperature? This is a simple Le Chatelier's problem. We know that it's exothermic, so if we add this heat into this side by raising the temperature, it's going to shift back that way. So the amount of NO will increase. Right? That will increase when we raise the temperature because we're adding that term and it goes that way. So there's a lot of blue smoke in this problem. A lot of stuff you don't need. All you need to know is
So we increase.
all you need to know is this. You need to know the sign on this one. It doesn't even matter what this is, just the sign. That means you put it on this side, it's exothermic. So if we increase the temperature, it goes that way. All right. I thought we did this one before. Second law of thermodynamics states that what? Entropy of the universe increases during a spontaneous process. Well, yeah, that's true. B?
It's not like the first. Is that like for 3?
Yeah, the first one, the second one we did.
It's literally the same question.
Is it?
The second law of thermodynamics states that on number 4.
Are the same answers?
Not the same answers, but it's the same.
Same question.
Same question.
Okay. It's just asked a different way.
Ask.
Yeah.
You know, I'll take it.
So 40 is B. I'm not even going to write that one up there.
Get it or you don't. Get it the first time or you don't get it all.
Yeah. Let's look at 42. A mixture of hydrogen and chlorine remain unreacted until it is exposed to ultraviolet light. Mixture of hydrogen and chlorine is stable until we add ultraviolet light. Then we get the reaction that gives you that. And this is supplied by a burning magnesium strip. So magnesium solid plus oxygen yields magnesium oxide solid. So that'd be 2 here, 2 here. And that gives you this energy. Right? So actually, what are we doing here? Right?
Adding,
Yeah, if you've got this energy and this is the reaction progress, then you're adding energy
this one,
to go like that. So the hydrogen and chlorine are over here, and hydrogen chloride is on this side. So the ultraviolet light is providing the activation energy, right? This is UV from that reaction. Okay. All right. Okay. Delta G is negative, delta H is negative, delta S is negative. So each one of these is negative. Delta G is negative, delta H is negative, and delta S is negative. Okay, we can't deduce delta S negative from this because 1 and 1 is 2 and 2 here. So this has to come from, they have to tell us this one. But this negative delta H means that we've got heat on that side, and I drew this correctly, right? It went from this level energy down to this level, and the difference here is delta H, which is negative. Okay. Delta G tells us that the reaction is spontaneous. It will go. So which of the following is, yeah, go ahead.
delta H negative if there's activation, like if there's energy being the UV.
Well, the delta H is a state function. It only depends on what this level is and what this level is.
Okay.
Doesn't matter what happens in between.
Okay.
Right. This is equilibrium. This is kinetics.
Okay.
Okay. Okay, so let's look at our choices. The reactants are thermodynamically more stable than the products. No. The reactants are at higher energy, so they're not more stable than the products. Right? So A can't be true. Because if you're at a higher energy level, that implies instability. Right? These two separate are unstable. Right? So that one's false. B is the reaction has a small equilibrium constant. Well, actually, we would need the values for equilibrium constant. So the equilibrium is delta G equals minus okay, RT. Took me a second. Okay, so if we put the delta G in here, which is equal to 4554, negative 4554 kilojoules. Right? So this is going to have to be converted to joules because that's in joules. So this would be negative 45,540 joules. And I'm going to take this one over here, say minus 8.3145. And I'm also going to take the temperature, which is, I guess it's standard temperature, 25, 298 K equals log K. So let's see what that value is. 45, 540, 8.3145, and 298. So that's 18.38 equals log K. And then K is equal to E to the 18.38, which is, whoa, 9.6 times 10 to the 7th. So if it says the reaction has a small equilibrium constant, it has a huge equilibrium constant. All right, so this one's false. The ultraviolet light raises the temperature of the system and makes the reaction more favorable. Well, it didn't tell us it raised the temperature. It just says it supplied the energy. Ultraviolet radiation supplied the energy. We can't say that the temperature was changed. Right? There's no indication that the temperature was changed. Right? So I have to call this one false on its face. There's no evidence that the temperature was changed. The negative value of delta S slows down the reaction. Negative value of delta. Wait a minute. The key there is slows down.
Speeds it up.
No. This is thermodynamics, equilibrium. This is kinetics. Right? They don't have anything to do with each other. Right? So, right? So this was false because it's mixing apples and oranges. Right? This one talks about that. This term in there talks about this.
That's the kinetics, but activation.
Yes, kinetics, activation energy, right. So by process of elimination, E should be correct. Let's see, the reaction is spontaneous. Yes, spontaneous. We know that because delta G is negative. And then the other part is, but the reactants are kinetically stable. Well, yeah, this reaction doesn't happen unless you add the activation energy. So the reaction may be thermodynamically favored, but it's not going anywhere until you get activation energy. So the kinetics say that it's stable. You have to add this much activation energy to get it going. So E, yeah, E is your best answer. I mean, we went around the barn 3 or 4 times to get that answer, but that's it. Okay. That was 42. Let's see, which one else did I pick out? Oh, 51. Okay, 51. Consider the gas phase reaction NO plus 1/2 O2. NO plus 1/2 O2 of these gases. They don't write them as gases, but I'm sure they are. Yields NO2. And delta H is minus 56.91. We did this before, didn't we? Delta H0 equals minus 56.91 kilojoules. And K equals 1.46 times 10 to the 6th. Yeah, at 25.
Why'd you say they should always be a gas? Why'd you say that? You should always be?
Well, I just know that nitrous oxide's a gas.
No, I mean, before you said that, you should just write them as a gas because.
Yeah. The reason I want to write them as a gas is because when we start talking about reactions that where bonds are broken and formed, then if we have liquids and solids involved, you have to account for energy that's involved in phase change.
Okay.
But if they're all gases, then you're talking about bonds only. Yeah. Okay, calculate K for the following reaction at 25 degrees. So we want the K for this reaction, NO plus O2 yields 2NO2, right? Oh, this isn't as difficult as it looks. When you multiply, what did we do to get there? We multiplied that whole thing by 2, didn't we? 2 times a half is 1, 2 times that is 2. So what happens to the K when you do that? When you multiply times a factor, that factor becomes the power of K to give you the new K. So that would be 1.46 times 10 to the 6th to the second power. We just have to square it. Right? It's like when you add equations together to get a final equation. The K's multiply times each other. So it's like we're adding one of these and one of these. So we have a K times a K, which is K squared. 1.46 exponent 6 and square it. So that should be equal to 2.13 times 10 to the 12.
So those are H's are K?
I'm sorry?
Those H's are K?
No, we don't even need that.
Oh, what is the?
This is what we're looking at right here. That's the K for this reaction. And this is that reaction times 2.
So then 1.46 times 10 to the 6th, just square it.
Square it, yeah. Mhm. Yeah. When you multiply, when you multiply an equation by a whole number to get the next equation, the K that's associated with the next equation is, yeah, that value is the power of K.
Okay.
If we took a half of it, then we'd say a half or the square root of it.
But it doesn't matter, it's still the same, it's just the next.
It-
Thing, right? Like the K,
This K is for that equation.
yeah. It don't
This K
change.
is for that equation. Yeah, there's a lot of information in there that you don't need. And it looks more complicated than it is. That just confirms my conclusion that word problems are designed to confuse. That's their main purpose. Okay, let me get, this is in my way. Let me get this out of the way. There we go. Okay, the equilibrium constant of a certain reaction was measured at various temperatures to give the plot below. So we're plotting natural log of K versus 1 over T. All right, I have to look up that, the formula for that straight line is this number 52. Natural log, well,
It's,
natural log of K equals
it's at 1.
1 over T, which would be times delta H, negative delta H, 0 over R. I'm trying to remember now, plus delta S 0 over R. I think that's the right equation. Let me look it up and be sure.
For the,
Yes, that's right. This is the Van Hoff equation. I don't know if I told you that during the lecture.
I don't think so. I thought it, I didn't know, I thought you was talking about something else. I was going to guess, but I was like, I thought you was talking about something else. I was going to be really wrong.
Okay, so what's the delta S for this reaction in joules per mole? All right, the delta S, right? We want the y-intercept. So where's the the y-intercept is 3. Right? So 3 is equal to delta S0 over R. Right? The y-intercept, this is the y-intercept, right? Y equals mx plus b. That's the y-intercept. So we look at the graph and we find the y-intercept is 3.0. And that's equal to this right here. So this value is 8.3145 joules per K mole. And if we take that and multiply it times 3, then we get 24.94 is 3. 3 is
Says the equilibrium constant of a certain.
delta S0. Well, the units for delta S have to be joules per K mole. Right? Reaction in joules per mole K. Yeah, K mole. So they rounded off to 25 to 2 significant figures, probably because this is 2. Right, so this should be rounded off to 25. Okay. That's just checking to see if you recognize the equation that goes with that graph and can read information from it. That's the purpose of that question. All right. 56. Equilibrium constant Kp in atmospheres for the dissociation reaction of chlorine into 2 chlorine atoms was measured as a function of temperature. A graph of Kp, natural log Kp versus 1 over T for this reaction gives a straight line with a slope of negative that value and an intercept that value. The value of delta H for this dissociation reaction is, okay, here again, we're looking at the natural log of K equals the negative delta H over R times 1 over T plus delta S over R. So if they're asking us what's delta H, then we want to find out what's the slope of that line, because that's what the slope is. And the slope says it's negative 1.651 times 10 to the 4th. And that's equal to negative delta H over R, which is 8.3145. So if I multiply this, which is joules per K mole, multiply that times this value.
Slope.
Huh?
But even the slope. Or
This is the slope. And this is the expression for the slope right here.
Oh, so does that give you
So
the H?
yeah, so I set the slope equal to that, and then I take the negative along with this over here, so now it's a positive.
Okay.
1.651 and divide by, multiply by 8.3145. So I get delta H equals 1.373 times 10 to the 5th joules per mole. And the answer is in kilojoules. Right? So this would be 1.373 times 10 squared kilojoules per mole. And it looks like they have it in standard notation. So we got to say, all right, if that's, take this 100 times that, which is 137.3 kilojoules, which is B. And it's positive. So for this reaction, we had to put energy in to make that transition. Energy had to go in to break that bond and make these two free atoms. So that makes sense. '57. Okay, for a certain process at 300 K, temperature equals 300 K. Delta G is minus 12.2 kilojoules. Minus 12.2 kilojoules, is that what it said? Yeah. And delta H is minus 7 kilojoules. Okay. If the process is carried out so that no useful work is performed, delta G is what? Oh, this was too easy. Delta G is equal to the maximum amount of work that you can get out of a process, right? Maximum amount. We're carrying, yeah.
If negative, it's spontaneous, right?
Yeah, it's spontaneous. And we can get that much work out of it. Maximum. But what they're telling us is that the process is carried out so that you don't get any useful work out of it. And then the question is, what is delta G? Well, just because you didn't get any work out of it doesn't mean delta G is different. Delta G is the same as it was before. We just didn't get any work out of it. Okay? We lost all this maximum work to something, heat. All right? So delta G is 12.2 kilojoules. It's still that value, whether we got work out of it or not. All right? It's a trick question. Yeah, it's the same value. Oh, that's it.